All right, so in this video, we're going to be looking at applications of determinants, particularly those related to geometry. So we're going to be looking at ways of using determinants to calculate area and volume. So in general, there's two different ways that you can think of a problem involving area in two dimensions. We can think of it in terms of the points that define the place that we're trying to calculate the area for, or we can think about it in terms of the vectors that define the sides of our object. There are equivalent versions for both of these situations. So if we're looking at it in terms of points, then our determinant is going to be a 3x3 determinant. We're going to put our 3 points in the first two columns, basically, and then we'll have ones in the third component in order to make the determinant square. And then if we have vectors, essentially vectors would already be calculated in terms of the differences between any two of these pairs of points, then we can just put them into a 2x2 determinant. And then the determinant could be either positive or negative, so we would take the absolute value in order to get the area. If you switch the order, you'll change the sign. So the sign doesn't really matter. It's the magnitude that matters. Now, if you are trying to find the area of a parallelogram, you just use the determinant. But if you have a triangle is basically just half that parallelogram. So you can also use the same example to find the area of the triangle bounded by 3 points, or whose two sides are given by those given vectors, by just simply finding the area of the parallelogram and then dividing by 2. Now, there is an equivalent in 3 dimensions. So if we're dealing with 3 dimensions, we're trying to find the volume. And then the shape of a parallelogram is a parallelepiped. And basically, you think of it as a slanty box. And again, you may have 4 points that determine that parallelepiped. And if you have those 4 points, again, you put them in the first 3 columns of your matrix. You put ones in the final column. This is the 4x4 determinant. Kind of nasty to calculate, but if you use technology, again, you'll get the correct value. Take the absolute value. Again, the sign doesn't matter. If you have your parallelepiped bounded by 3 vectors, so again, we've already done the differencing between our coordinate pairs of points, then you don't need the row of ones or the column of ones. You can just put your vectors into a 3x3 determinant and calculate the volume that way. Now, what's nice is in a 3-dimensional case, if you cut off your parallelepiped, you get a tetrahedron. And so the tetrahedron is not half of the volume of the parallelepiped. It is 1/6 of the volume of the parallelepiped. And again, both of these formulas will work just fine, but calculate the determinant and then divide by 6. So let's walk through some examples. We can look at the 2-dimensional case graphically. So I've plotted these 3 points, and I can calculate this either as a parallelepiped. You can see that essentially, if I have this vector defining one side of my parallelogram here, and I have this vector here, then the opposite side would just be this vector translated over to start from this direction. That would be my whole parallelogram. Or if I connected my dots directly, that would be my triangle. So I'm going to go ahead and calculate the determinant both ways, just so that we can see they're going to give us the same thing for the full parallelogram, and then we can divide by half to get our triangle. So in the point case, we're going to calculate a 3x3 determinant. And we're going to put the points again in the first 2 components of our matrix, 2, -2, and then ones in the final one. And I'm going to use technology to do this calculation because I have another video someplace else that calculates the determinant by hand. And usually when I ask these kinds of questions on an exam, what I'm looking for is, do you know that this is how you calculate it? Not, I'm not looking for the actual calculation. If I want to the calculation, I'll ask you, show me the calculation by hand in another problem. Here, I just wanted you to set it up and then you can use technology to solve it. The determinant that I got from putting this in the calculator, assuming that I didn't make any typos, and I'll just double check again just to make sure. I got -15. And so the volume of the parallelogram is 15, not -15. And the volume of the triangle, or not the volume, it's the area. It's stuck in 3D. And the area of the triangle is 15/2, or 7.5. Now, if I want to do this by vectors, then I just need to calculate the differences between pairs of points. So, for instance, this is 1, 2. What is the vector that connects 1, 2 to 4, 5? So that vector so 4 minus 1 is going to be 3, and 5 minus 2 is also going to be 3. And then my second vector, I'm now going from 1, 2 to 2, -2. So 2 minus 1 is 1, and -2 minus 2 is -4. And so if I make my determinant from that, three, 3, 1, -4, then I get 3 times -4 is -12, minus 1 times 3 is -3. I also get -15, and therefore, again, the area of the parallelogram is 15 because it's the absolute value, and the area of the triangle is half that, which is 7.5. Now let's look at another example in 3 dimensions. Now this one obviously is more difficult to plot, but basically everything works the same way. So rather than retype my entire matrix, let's grab my formula. So the volume, we're going to put our points in here. So -1, 2, 3, -3, 2, 5, 2, 4, 4, 3, 4, -1, and then the last column is all ones. And so again, I'm going to use technology to find this determinant. It's always a good idea to double check that you haven't made any typos when you put these things in your calculator. And then my determinant, I get negative 16. And again, just if you change the order, you'll get a positive 16. The volume of the parallelepiped, again, your slanty box is 16. And if these were defining a tetrahedron, if these were the corners of a tetrahedron, the volume would be 16 over 6 or 8 over 3. Now, again, we can also have a vector version of this. And if I calculate my vectors between my corresponding points, it's typically a good idea when you're doing this to pick a point that's your corner and then calculate vectors from that one to the other 3 points. So we're going to go from -1 to -3. That's going to be -2 units, then 0, and then again, -3 minus a -1, 2 minus 2, 5 minus 3. Again, not the ones, because that's just making our matrix square, basically. And then 2 minus a -1 would be 3. 4 minus 2 would be 2. And 4 minus 3 would be 1. And then 3 minus -1 would be 4. 4 minus 2 would be 2. And -1 minus 3 would be -4. And so we'll put that together into our 3 by 3 matrix. So we would have -2. And you can put them in rows or columns. It honestly doesn't make any difference. Doing the transpose of a determinant does not change the value of the determinant. And in this particular configuration, I get 16. Again, the sign doesn't matter. And so I would end up with exactly the same answer I had before. The volume is 16, and the corners and the volume of the tetrahedron would be 16 over 6, which would be 8 over 3.